Hi, I'm Harsh Shah, and here is my video on Lab 2 Projectile Motion. The purpose of the lab is to compare observed motion in our experiment of throwing a projectile with two different computational models in VPython. And the main question is how accurately can these simple physics models using gravity or drag force and gravity in VPython compare to the actual thing. The physics concepts used in this lab are force of gravity, drag force, and projectile motion. Force of gravity, Fg equals mass times gravity, which is where g is 9.8 meters per second squared on Earth. Drag force, where b is the proportionality constant, the magnitude of velocity, and norm, and all these are multiplied. B is estimated to be 0.001 in our case. And in projectile motion, the movement of a projectile in a curved path as it falls to the floor, as seen, and that's in our experiment. And the system is shown to be the projectile, and the surroundings is the Earth. Here's kind of a visualization of how drag force, force of gravity act on an object in projectile motion. The kind of preview of the results is that we were able to find that the computational model following the ideal circumstance of having no drag force, we ended up overestimating the trajectory of the projectile in that case, but by adding drag force we were able to get pretty close to the actual trajectory, of course not equal. The experimental procedure of the lab was first we took a meter stick and we held it up, and then the subject used a projectile, which in our case was an AirPods case, and we threw it from the height of the meter stick, and it had upwards. It was thrown diagonally upwards, and this entire procedure was recorded on video, and then the mass of the object was recorded to be 27.9 grams. Here's a video of the experiment. This video is brought into the tracker software, and the clip settings were adjusted to remove excess at the start and at the end. The x-axis was set to the floor, and the origin was set right below the where the projectile was thrown from. The calibration stick was lined up to the meter stick that was in the video, and the projectile was set to as mass A, and then we tracked it frame by frame. And the data at the end of it was taken and put into Excel at the time, the x position, the y position, the x velocity, and the y velocity of the projectile. Here's a video of the tracker software. For the first model, only gravity was considered, so the ball's mass was declared and the net force of the on the projectile was calculated, and that was F net equals Fg, which is mass times gravity, and the velocity and the position of the projectile were updated using their respective update equations, which is final velocity equals initial velocity plus F net divided by mass times the time, and final position equals initial position plus velocity times delta time. Here is kind of how it was implemented in VPython. Here are the results of the Model 1 in VPython, where you can see the position and of the projectile in x-axis and y-axis over time, and its velocity on x-axis and y-axis over time. For Model 2, we considered both gravity and drag, so the F net was set equal to Fg plus F drag, and Fg was set equal to mass times gravity, and F drag was set equal to the proportionality constant, was also defined, times the magnitude of the velocity, times the norm of the velocity, and the velocity and the position vectors were updated respectively using their update equations. Here is how the Model 2 was implemented in VPython. The results were obtained, and here we can see the graph of the position and velocity of the projectile over time in the x and the y axes. All the data from the tracker software, the VPython for Model 1 and the VPython for Model 2 were taken and put into a spreadsheet, and then the data was put into a scatter plot. In the scatter plot, we can see the results of the tracker software, the Model 1 and Model 2 all plotted in the same plot. And here we can see that Model 1 overestimates the tracker by quite a lot, and then Model 2 is able to keep relatively a good track of it until the end, where it just slightly deviates. Sources of error for this lab can include that the proportionality constant is not calculated but estimated in our case, and if it were to be calculated, a more accurate result will be obtained. Tracking the projectile in the tracker software is manually done and may result in discrepancies from the actual motion, actual calibration measurements, and also there can be camera warping in the video. What does it mean question? The time to reach terminal velocity is quite a lot in usual cases, but in our case the motion was only for a short time. So if you were to use a better experiment, it would be to throw the object upwards, and on its way down, if we have a higher hang time, we're able to witness that the object reaches terminal velocity, where the drag force equals the force of gravity. What if question? If the initial speed was kept the same but the object was thrown up, straight up, it would remain in the air for a longer time and have a higher hang time, because it would have a greater y component of velocity compared to in our case, and that would result in it having a greater max height and greater hang time. Thank you.